All right, you guys are being recorded right now.
Hello and welcome. I'm Dr. Heather Johnston, publisher and chief editor of Power Engineering International magazine, and thank you for joining us here today. In today's discussion, we will be exploring how to improve the performance and therefore the economics of gas turbine-based power plants in Asia, and in particular, how dry air injection can help you achieve these objectives. According to the International Energy Agency, I'm not coming up on the screen when I.
And actually, I'm seeing you full screen, but
Okay.
I'm seeing you sway in your chair a whole lot.
Okay, sorry.
Lock that chair down.
Oh well, it's a swivel chair I'm on.
That's all right. That's all right.
Okay.
So I'm gonna have you start it again,
Yep.
and then just do your thing.
Hello and welcome. I'm Dr. Heather Johnston. I'm publisher and chief editor of the Power Engineering International magazine. Thank you for joining us here today. In today's discussion, we will be exploring how to improve the performance and therefore the economics of gas turbine-based power plants in Asia, and in particular demonstrate how the utilization of dry air injection can help you achieve those objectives. According to the International Energy Agency, Asia will be the second largest gas market in the world within 2 years, and gas-fired generation capacity will dominate more and more. However, there are continuing uncertainties here in terms of supply, export versus import, and also the construction of the necessary gas infrastructure, particularly in the ASEAN. Until these issues are resolved, and in order to meet the power demand in many of the rapidly growing economies in Asia, there will be a need to maximize. Oh, I've lost it. Sorry. Can I take it back to?
Yeah, just take it back a couple seconds.
Did I start from where until those issues are resolved?
That sounds great. That sounds great. And you're doing a good job looking at the camera, and you're doing a good job not swaying. I know there's a lot going on there. All right. Whenever you're ready.
Until these issues are resolved, and in order to meet the power demand from many of the rapidly developing economies in Asia, the option to upgrade existing gas turbine-based plant in the most cost-effective way will be a priority. And to help us explore this idea, I'm delighted to introduce to you our two speakers. Firstly, let me introduce John Sasso, who is a senior consultant at RTT Sigma Consulting. Oh, sorry, John, it's engineering, isn't it? I do apologize.
Just take it back from, I'd like to introduce my two speakers.
And to help us explore this idea in more detail, I'd like to introduce our two speakers to you. Firstly, let me introduce John Sasso, who's senior consultant at RTT Sigma Engineering. John has, for more than a decade, been offering asset optimization services to clients to improve their reliability, efficiency, and profitability of their power plants. He has also been heavily involved in providing owner engineering services to developers, plant owners, and operators. John's company was recently involved in a study for Indonesian Power, which with an installed capacity in excess of 9 gigawatts is the largest power producer in Indonesia. The objective of the study was to look at how to improve the performance of Indonesia's power existing gas turbine-based plant or fleet, and this involved evaluating several options, which resulted in an increase in the power output from the machines. Today, John will be taking us through the study and will be sharing its major findings. Today's second speaker is Steve Quisenberry. Sorry, Steve, have I pronounced your name correctly? I meant to double check with you. Quisenberry?
The second pronunciation, Quisenberry.
Quisenberry. Sorry about that. Let's take it back to the second speaker. Yeah. And today's second speaker will be Steve Quisenberry, who's Vice President at PowerPhase. Steve has over 17 years experience in advanced engineering, particularly in turbine engineering. He started his career as a test.
Heather, I'm going to stop you there. Sorry.
Yep.
You're swiveling again. You're dancing in the chair. So we'll take it back from our second. Sorry, I know this has got to be frustrating. You got all these eyeballs watching you. We'll pick it back from when you introduced Steve. So our second speaker. And let me mute myself, and whenever you're ready.
Our second speaker today is Steve Quisenberry, who's Vice President at PowerPhase. Steve has more than 17 years experience in advanced engineering, particularly in turbine engineering. He started his career at Pratt & Whitney and advanced to General Manager at Alstom Thermal Service Middle East Operations. Steve's presentation is going to dovetail nicely with John's, and in his presentation he's going to demonstrate why dry air injection can help you improve the performance as well as the cash flow for gas turbine-based power plants in Asia. He'll also share with us some performance data for PowerPhase's system installed on a 6B and 7FA turbine. And with that, I'd like to invite John to take the floor. Right.
Good. Okay. So John, are you there? I see you're still muted. Oh, you're still muted.
Okay, can you hear me now?
Yep. And then Heather, I'm going to have you mute yourself here, and I'm going to mute as well. So Heather's just introduced you, John.
Hey, one thing is Heather still labeled or mispronounced our company. It's RRT Sigma Engineering. I think she said RTT or something else. So we may have to redo that little clip.
Yeah, let's do that now if that's okay, Heather, just so we don't get lost in it. I don't remember exactly where that was at, but you're still muted. And then John, I'll have you mute as well. Cool.
So firstly, I'd like to introduce John Sasso, who's a senior consultant at RRT Sigma Engineering.
One more time, just for insurance.
Okay. Firstly, sorry. Firstly, let me introduce John Sasso, who's senior consultant at RRT Sigma Engineering.
Good. Okay. So then, Heather, you'll mute. John, you'll come in and go ahead and talk a little bit, John, so it switches already.
Okay. So here we have, thank you, Heather, and good morning. As Heather pointed out, a study was conducted to compare various alternative gas power enhancements for the power plant in Indonesia. The Pensinggaran site in Bali, Indonesia, which has 4 simple cycle gas turbines, was chosen as the sample site to perform the technical comparison. In the first slide, we see a typical performance curve of showing gas turbine power output and heat rate and exhaust flow as a function of ambient temperature. The green line in particular is what we're here really to talk about. With the high ambient temperatures, we see that there's a significant loss of power. We want to recover that power as much as we can to utilize the full capabilities of the gas turbine. So we're going to evaluate we're going to evaluate 6 technologies, and the 6 technologies are evaporative cooling, inlet fogging, inlet chilling, wet compression, dry air injection, and humid air injection. We'll go through each of these one at a time. So in an evaporative cooling system, a wet cooling media is inserted in the inlet of the gas turbine filter housing. It's a passive process, as the air going into the gas turbine is drawn over the evaporative cooling media. The media is kept wet. The media is kept wet using high-quality water, such as that from a reverse osmosis unit. The air entering the filter house passes over the saturated media, and the water contained in the media evaporates into the airstream on its way to the gas turbine. The extent of the evaporation, though, is inversely proportional to the percent humidity in the air. That is, if the humidity is high, it's hard to evaporate more water into it. Considering the climate of Indonesia, this was not a favored alternative because of the already high 85% average humidity in the area. But we present it nonetheless because other areas might have an interest in utilizing it. Also, evaporative cooling is limited in its application because it does not work when it's raining out, when it's very high humidity. The second system we looked at is a fogging system. Fogging is an active form of basically the evaporative cooling system. In fogging, we insert pressurized water to spray into the airstream using ultrafine droplets of approximately 10 microns in size. The amount of water spray is typically a little more than 100% of that needed to achieve saturation. The excess water compensates for the residence time so that 100% effectiveness can be achieved. Fogging has the same attributes and limitations as evaporative cooling, but with virtually no additional inlet pressure drop. Since wet media is not used, we only have these array of spray heads. A small amount of parasitic load is required to create the pressurized water, and while the overspray conditions of fogging are more likely to approach the saturation condition, that extra water can present a problem, especially in retrofit applications, because the extra water will literally drain on the inside walls, collect dirt, and virtually get sucked into the gas turbine, which fouls the gas turbine and degrades the machine. So since fogging systems are water droplets, the water must be demineralized prior to injection so that the dissolved minerals do not react with the gas turbine materials downstream. Fogging systems do have an advantage of being online very quickly. The next system we looked at is wet compression. In an application using wet compression, demineralized water is injected at high pressure very close to the inlet of the gas turbine or in various stages of the gas turbine compressor. The water nozzles create an ultrafine droplet-sized water mist. At the inlet, some of the water evaporates quickly, cooling the inlet air similar to evaporative cooling or fogging. However, the water injected above that needed to achieve saturation is drawn into the compressor blade path purposely and evaporates during the various stages of the gas turbine compressor. Wet compression has the advantage of providing the effective interstage cooling as it evaporates in each stage of the compressor. Evaporation of the water droplets in the compressor blade causes the air temperature to drop and thereby reduces the power consumption of the compressor because less energy is required to compress cooler air compared to the warm air with the same mass. This translates into a decrease in turbine work because of the intercooling effect. The result is more turbine power for the generation of electricity and improved gas turbine efficiency. However, in this system, water that does not completely evaporate impinges on the compressor blades and can easily cause pitting and premature damage to compressor blades, particularly leading edges. When an early stage of a compressor fails, the broken pieces go downstream, resulting in a really bad, catastrophic repair bill and many weeks of repair time because of the downstream damage that could occur. Therefore, proper applications require compressor blades and the stators to be coated to protect the surfaces of the steam and water impact. Siemens uses an advanced compressor coating on gas turbine hardware to minimize the damage of wet compression. Maintenance is also critical. As the water nozzles foul, the droplet size can increase, which result in water droplets impacting the compressor blade, which is not desirable. The pump discharge is connected to a compressor inlet system. Let me skip that. All right. Our next system that we evaluated was inlet chilling, and with inlet chilling, a cooling coil is installed in the cross-section of the gas turbine inlet filter plenum. Cold water, generated from a separate source, is pumped through the coil as the gas turbine inlet air flows over the coil. The advantages of inlet chilling is that the ability to reduce the inlet of the gas turbine to a desired temperature, generally at ISO conditions, 59 degrees usually, or even slightly lower during all times of operation. However, a separate source to create that chilled water is required. The chilling system can be an electric-driven chiller or an absorption chiller, and as you know, chilling systems require the heat be rejected to another source, which is usually a cooling tower, and that requires makeup water and water chemistry as well. The wet cooling tower uses the wet cooling tower uses the vaporization of water to the atmosphere to take away the heat of the cycle, driver, and the cooling effect. One of the disadvantages of inlet chilling is the permanent pressure drop in the inlet filter house that will permanently reduce the gas turbine output year-round, regardless of whether the inlet chilling system is operational or not, even during part load operation when the system is offline, when the chilling system is offline. Inlet chilling systems are generally very slow at responding due to thermal inertia of the warm water sitting in the piping before startup. One method to avoid this is to add a very small chiller to run 100% of the time to simply keep the chilled water piping system cold. However, this is a constant parasitic loss. Another system that could add power augmentation is steam injection. In this system, steam is injected at the combustor, and the pressure of the steam must be high enough to match the compressor discharge pressure. A source of the steam is required, usually from the heat recovery steam generator in a combined cycle or steam turbine extraction in a combined cycle. The steam is 100% lost to the atmosphere as it proceeds through the turbine and up the stack. Therefore, use of steam injection requires a demineralized system adequate to provide for the makeup water volume lost to the steam injection system. Water and steam, as with air, controls the flame temperature and does result in some lower NOx emissions. Steam injection normally is only attractive, though, when it's being generated in a combined cycle, or free steam might be available from some other source, such as waste-to-energy facility nearby. The introduction of water or steam in the blade path of the gas turbine will impact the chemistry of the turbine components to various degrees. Depending on the source of the steam, steam injection can be slow in reaching full benefit, sometimes as much as 1 hour for the steam to materialize. Steam injected is not considered at the Bali site because there is no steam capability. There was just simple cycle gas turbine applications. Our next system that we looked at was an air injection system. Air injection has a separate standalone air compressor designed to match the gas turbine compressor discharge conditions. The system can be with either humid air or dry air. I'll turn the floor over to Steve very shortly to describe in detail the dry air injection system, but let me briefly talk about it. The dry air injection system uses atmospheric air, less the moisture that condenses in the compressor cooler, and The dry air system can respond quickly to power demands coming online in less than a few minutes. Dry air introduces no additional chemistry concerns as with water or steam injection, and therefore the life of the gas turbine components is not impacted. The dry air injection system is very portable and introduces the extra air at the compressor discharge before entering the gas turbine. Humid air, on the other hand, can be considered as a combination of dry and steam injection working together. The humid air injection is essentially a combination of high pressure steam injected with diluted with the dry air injection system. Humid air can provide a little more output than the dry air, but at less efficiency because you're losing all that heat of the steam going up the stack. Steve, I'd like to now turn the floor over to you to better describe the dry air injection system.
All right, Steve, go ahead and say something just so I get you on the screen.
Yep, is that good?
That's good, and you comfortable how you're talking there? That's where you're going to sit?
Yeah, it gets me closer to the microphone.
Okay, that looks good. So I'll let you do your thing, so then you can just say thank you or some kind of segue there, and then I'll get out of here.
Okay. Thank you, John and Heather, for the introductions. My name's Steve Quisenberry with PowerPhase, based out of Florida here in the United States. We've developed a patented dry air injection system, which is the world's first commercialized dry air injection system, which we call TurboPhase. As we go through the details of TurboPhase module, I'm going to show you how it functions.
Sorry, I'm going to have to stand back there. Hey, John, can you do me a quick favor and mute your microphone? Because I just had it switch over. Sorry, guys.
I'm sorry.
That's okay.
Get to that screen.
That's why we're recording, so we can go back. No worries.
Yeah, how do I get that to the screen back?
You click on the Google Hangouts tab, the web browser, and it'll be in the top left. It'll have a little microphone with a slash on it.
Yeah, I can't. Where the hell? The web browser disappears, and It's like I open Explorer and it doesn't. It's not in the link. It doesn't say it's open. Got to do this the long way. Sorry.
It's okay. What browser are you using?
The only issue is that
Explorer. Okay. Okay, got it. Join. Take me there. Okay.
What happened? What was the problem?
Oh, there it is. He's muted now.
Okay, perfect. So then, if you could, Steve, kind of just give me the introduction. Thank you, Heather. Thank you, John.
Sure.
And I'll leave you now. So just whenever you're ready.
Okay. Thank you, Heather. Thank you, John, for the introductions. Here at PowerPhase, we've developed and patented the first commercial dry air injection system, which we call TurboPhase. I'll go through the details of our TurboPhase module system, how it functions, and present some installation data from a GE6B site as well as a GE7FA site. As we go through this and address the questions that John mentioned, I'll compare it to the other technologies as well. So on the first slide, why TurboPhase? We reviewed all the existing products on the market, and we sought to develop our TurboPhase system to address the gaps or the holes we saw in the key principles. So first we wanted to maximize the existing power plants and use all that recovered energy that's missing on hot days, high elevations, high humidity situations. Secondly, we wanted to make it fast responding so it could be used as peaking power and enable renewable integration. As sun and wind fall off, you have to bring gas turbines online to recover that energy. Also, we want to be independent of all ambient variables, temperature, humidity, and elevation, as well as we had to be dynamic. Frequency control and small microgrids, we needed to be able to make sure we can maintain that frequency stability. And then the elimination of spinning reserve was key. The gas turbines that operate at part load are losing heat rate or efficiency because they're operating at part load to allow room to increase load as demand goes up. With turbophase, you can operate your gas turbines at base load and still have that immediate peaking need to accommodate that spinning reserve. And then finally, we want to take care of the environment. We're burning natural gas, we're using no water, and our NOx and CO are below what the gas turbine is producing. So on the next slide, we talk about, John mentioned the temperature effects. Here's a standard OEM curve showing how output and heat rate are adversely affected as temperature goes up from 0 to 120 Fahrenheit or minus 18 to 50 C. That's experienced in every gas turbine. With turbophase, we are offsetting that reduction in losses and bringing that ISO day output, that 15 C output, back on the 50 C day. We do that by putting more air into the gas turbine to replace the missing air, the missing mass density that occurs on hot, humid, or high elevations. So speaking of elevations, same correction curve you get from your OEM on your gas turbine shows an elevation correction effect. You basically are losing 30% of your output at 8,000 feet above sea level. Again, with turbophase, we can bring you back sea level performance up to 5,000 feet above sea level. This is, again, just replacing the missing mass density that goes into the gas turbine that your gas turbine cannot do with a fixed volume axial flow compressor. With the block diagram shown on this page, you can see that in the blue box, our turbophase is what we happily call the blue box. Our blue box has a reciprocating engine, a compressor, and a recuperator or a heat exchanger. Within that unit, we basically take and produce hot compressed air that looks like the exit of your gas turbine compressor. So it's pressure and temperature matching your compressor discharge that gets injected into your gas turbine before the combustion process, which then flows through the turbine, making more power. Your gas turbine knows what to do. It adds fuel, we add the air, you make more power, and in a combined cycle application, you actually make more steam, and therefore you increase your steam turbine output. In order to do this, this couldn't be an R&D project. We needed to make a commercial product that the customers could reliably use, that's driven to run for a long time, and is aligned on maintenance intervals with the gas turbine. So we basically went out and used standard commercial off-the-shelf components. Our engine shown in this picture is an MTU 2,000 kilowatt, 2,750 brake horsepower, 20 valve engine, driving a gearbox, which then drives a Hyundai 4-stage intercooled compressor. And that's shown in this picture without the sound and weather enclosure, which is then fully assembled in the factory and shipped to site completely finished. In doing so, we can use systems that keep the cost down due to volume of production, and also allow for an ease of maintenance. In general, our maintenance program it's an engine, so it's oil changes every 1,500 hours. Every 21,000 hours of operation is a minor overhaul, and 63,000 hours is a major. So if you ran at 4,000 hours a year, that's 16 years before the major overhaul. Again, it is an engine that's reliable, meant to run continuously or start and stop. Typically, these engines are used in everything from marine applications. The U.S. Coast Guard uses this block explicitly, to large mining vehicles, to gensets. Here on the next slide, you can see a few pictures of an installation showing the finished module being delivered to site. The modules, as I mentioned, are standard. There's no customization for each site. That way it keeps the cost down and makes the maintenance more friendly. They're fully tested. They come in a standard container-sized package. And when we bring them to site, with the piping, civil work is done ahead of time, and when the unit arrives, it is 3 days from the date of arrival to the date of fully commissioned and commercial operation. The site shown here is a site outside Chicago, and it's a GE6B site. You can see the trailer arriving. It is a 50-ton object being offloaded by a crane onto a foundation, and the finished picture in the bottom right. On that site, we had 2 of these units installed, 2 of our turbophase modules, or our blue box as we call it. And you can see the picture here showing the side, the recuperator on top. Inside the module, the engine's on the right, the compressor's on the left, and the item is a 40-foot standard container size. Here's an overview of this site outside Chicago, and what you see here is 2 turbophase modules connected to 3 gas turbines. As a modular system, we can connect any number of modules to any number of gas turbines. That way the plant operator can choose where to put the additional air and therefore the additional power and the heat rate improvements. When you do that, this gives the most flexibility to the customer. So in this case, this customer runs 2 out of 3 of their gas turbines every day, but they rotate which 2 they run. So by installing a system like ours, they can direct that power and that heat rate improvement to the 2 that are being run that day without buying a system for each gas turbine. And so when we do that, it's integrated into the plant in a small footprint. You can see on the slide the footprint compared to the chiller that's sitting next to it. This site also has chillers on it, and we're about 1/3 of the footprint required for such a system. One of the very things that we dove into and we needed to make sure of is when we install this system, we do not want to modify a customer's gas turbine. Our background here at PowerPhase, we are gas turbine designers. We don't see it as a challenge to modify gas turbines. Customers don't like us poking holes in gas turbines. So what's the nice thing about gas turbines is typically they all have an external pathway to the compressor discharge cavity. You can see in this picture on the left is a 7FA with a T and a valve welded into a line. That line is the OEM inlet bleed heat line. That line connects to the compressor gas discharge of the gas turbine. Our injection part is that valve. So we added that T in that valve and we connect a pipe to the other end of that valve. Same picture on the right is a GE6B. Again, it's a T in a line outside of the enclosure, which makes minimal impact to the site, minimal impact to the gas turbine, and this is what allows us to install this in days. We don't have to have an outage or modify the gas turbine. This exists on Siemens, Ansaldo, Alstom, GE gas turbines, vintages and sizes all the way down to frame 5s, all the way up to the latest J and G machines. With controls, we integrate all the controls into the existing DCS. The point here to be made is that there are no changes to the gas turbine controls. The gas turbine knows what to do with more air. Same thing happens when a cold front and your weather changes and it gets cooler outside. The gas turbine knows to add more fuel. Here in the same situation, depending on what the OEM is and how the engine's controlled, the gas turbine knows what to do with more mass flow. So there's no changes to the gas turbine. We provide the controller, the operator, with a new HMI interface to operate the turbophase modules. And so that way it's set up similar to the gas turbine. It's a megawatt demand, and then our turbophase control system determines what to do, what settings to put the gas turbine at, and what settings to put the turbophase module at to achieve that megawatts. So it's very unobtrusive, very easy from an operations, and very aligned with the current operation programs at existing power stations. Here's some data on a 6B. So a smaller machine. I showed you the picture from Chicago. Those are 3-on-1 6Bs. What you see here in the blue line is ambient temperature, and on the orangish line is output of one gas turbine. Going from 31 megawatts to 34, up and down 3 times. That's us turning a turbophase module on. Right? The power comes on instantaneously. The gas turbine reacts in milliseconds. And then what you see on the far right side is turning one module on, followed by a second module. So this was a little over 7 megawatts on a 31 megawatt machine at that given temperature. Our power is the same at all ambient temperatures. That 7 megawatts is the same whether it's 40 degrees Fahrenheit outside or 140 degrees Fahrenheit outside. Because the turbochargers on our engines allow us to make the same mass flow, we inject that same mass flow into the gas turbine. So this is a constant output across all temperature ranges. Here recently, in the last few weeks, we completed a 7FA install. Here's data on the 7FA. Again, the orangish line is ambient temperature, a little backwards on the colors, and the blue line is the outputs, and you can see the one turbophase module turning on and off. This was done, and you can look at the temperature on the right on an extremely hot day, and with that temperature, we were able to add 4.5 megawatts per module, which results in 22.5 megawatts on a machine that was making 120 megawatts. All right, so again, a 20% power increase on and off instantaneously, again demonstrating that this occurs at any temperature. So on these units, it's it's 110 Fahrenheit, 115 Fahrenheit outside, demonstrating this performance. Since everyone has different gas turbines, I thought I'd give you a summary of the different frames, output and heat rates, number of modules required. The number of modules changes because the gas turbines are different sizes. So on a 6B that makes 30 megawatts, 40 megawatts, we put one module. On a 9FA, that's a 200 megawatt, 250 megawatt machine, we put 6 modules. And each module is the same, and we just gang them together in a common header. Our goal is to put 5% mass flow into the gas turbine. That 5% mass flow is what's accepted by the OEMs and is in line with the changes in mass flow associated with ambient temperatures. So kind of looking at the benefits on the turbophase, to recap it, the ambient independent allows the customer to recover the missing energy from their existing gas turbine. Your gas turbine loses 20 to 30% at temperatures and elevations. We recover all that back to ISO day conditions at all ambient temperatures. The fast response side, depending on the market you're in, allows for spinning reserve, allows for fast start or dynamic signal capability or frequency control. All this can be done. The unit starts fully from cold in less than a minute, and when it's online, it's millisecond response. So when it's online, it essentially can be used as regulation or as a battery on reducing and gaining load. And then when it's offline, it can come online to support renewables falling off. Sun goes away, wind goes away, you can bring on turbophase in that 60-second period. And then environmentally friendly, we consume no water. So unlike some of the other alternative technologies that John discussed, you do not require water, and we have a SCR capable and CO catalyst capable system. Naturally, we're burning gas, so we're 42 ppm NOx, but it can be reduced to sub 4 ppm. And then on the other side is the gas turbine, right? You do not want to add an augmentation technology that causes you to damage your gas turbine. Injecting droplets of water into a gas turbine can be damaging. We inject no water, no steam, therefore there's no maintenance penalty on your gas turbine. And then finally is the return on investment. All the power producers in the business to make money. As we do this, we're adding more capacity, so you're getting a bigger gas turbine on a hot day, more energy because you can turn the system on and sell the energy in a fast response. And then also in some markets, there's ancillary services such as regulation control, reserve margin, speed of response. And there's also, we do have also the ability to put on a black start generator with the system to allow the same system to be served to black start the gas turbine to start without shore power, as we would call it. So those are kind of the benefits of turbophase. We shared this with John and RRT Sigma for their analysis. So at that point, I'll turn it back over to John to go through the results of the analysis.
All right, Steve, so you can go ahead and mute, and then John, I'll have you unmute and say something so it'll switch for you.
Okay, terrific.
There we go, and then I'll let you take it from there.
Okay, thank you, Steve. So as we talked earlier, the evaluation was done for a particular power station in Bali, Indonesia, which had 4 simple cycle gas turbines. We'll go through, just describe our procedure and talk about the results. They had an Alstom. They had 4 simple cycle gas turbines, an Alstom Atlantique 21.35 megawatt installed back in 1985, a GE MS 500L rated at 20.1 megawatts installed in 1993, and 2 Westinghouse 251Bs rated at 42 megawatts each. Our basic procedure was to visit the site and obtain the latest post-overhaul gas turbine test results that they have done in the field. We were able to then compare these test results to the original OEM design power output. We then replicated the new and test results in GT Pro. GT Pro is a gas turbine and combined cycle modeling software. We applied each of the gas turbine enhancements one at a time: evaporative cooling, inlet chilling, wet compression, dry air injection to each of the gas turbines and calculated what we predicted to be the impact on the output and heat rate of the 4 gas turbines. And here's a results table. So we can see that for the combined 4 units, we looked at first section was first cost, and while the absolute first cost was cheapest with fogging, the next section talks about evaluated additional net power output, which is row 7. And we see that although the wet compression provided the highest power output, dry air injection provided for the units that were studied the second highest power output. When we looked at the installed capacity per kilowatt, and that should be kilowatt. Installed capacity cost per kilowatt, which is row 8, the dry air injection system was second to the wet compression. So the lowest installed capacity cost was with the dry and wet compression systems. When we looked at other factors such as lead time, installation time, downtime, and fuel consumption, we looked at incremental heat rate, and again, the incremental heat rate was very attractive for all of the systems studied, except for the inlet chilling. Inlet chilling was very high. So when we go to our next slide, we now looked at the operating cost, and the operating cost, we selected certain baseline assumptions such as fuel cost, fuel heating value, and operating hours per year. And when we looked at the various alternatives that would provide incremental power, that could provide incremental power to the facility, we found that the dry air injection resulted in the lowest average power cost of $0.185 per kilowatt hour consumed. And the capacity cost, as we said in the previous slide, was $5.73. Now, when we take into account the alternative options, evaporative cooler was definitely out of the question because of the high ambient humidity, so there wasn't much power to be gained with that option. Similarly, fogging created similar limitations because of the wet ambient conditions that were used at the site. Chilling was very capital intensive, so it resulted in a very high capital cost per kilowatt hour. And humid air injection was really not practical because of the lack of steam being produced at the site. These were simple gas turbines. So similarly, when we looked at the impacts of the wet compression, the potential installation time, the coating required to be applied to the gas turbine, the additional downtime that would be required to install the system, as well as to install the coating on the gas turbine, protect the gas turbine components, and the potential for damage from the wet droplet damage, we concluded that the dry air injection by far met or exceeded the expectations of any of the alternatives. Dry air injection had the least overall operating cost and a very good capital cost. It also allowed them tremendous flexibility to be able to install 3 modules and operate them on any of the 4 gas turbines. And this was only a limited application where we looked at 1 turbophase module per gas turbine, but in analysis, we think more power could have been generated even with an addition of another power phase module. So in conclusions, the analysis showed that the dry air injection offered overall the best alternative for the Penson-Garren-Bally simple cycle gas turbines, in addition to the lowest operating cost per kilowatt hour and lowest capital cost, let me try that again. In addition to the lower cost per kilowatt hour for operating and lower capital cost, the benefits of the dry air injection, we concluded, had a short time to install, low capital cost, and introduce no additional contaminants into the gas turbine that might be had with the other systems, and has the portability to relocate the system on any other or future gas turbines that might be installed at the site, because they were thinking of additional gas turbines in the future. So they would be able to save basically these turbophase modules, upgrade or change their gas turbine to a larger unit, and be able to apply the turbophase modules to the replacement gas turbines for the future. So we concluded that that was the best alternative for them. Some additional notes I'd like to mention is that not all technology are mutually exclusive. In this application, we looked at one at a time, but for example, evaporative cooling can work with dry air injection together, so that they're both augmenting the power output. However, as we said, the high humidity conditions at Bali, evaporative cooling did not look favorable. Gas turbines also have typically large flow tolerances of about 5%, and this can easily be verified as the peak gas turbine output airflow at its cold temperature operating peak. So for this particular installation, we could have fine-tuned a little bit more the output of the TPM modules to further enhance and provide more power output to the Bali site. Okay, that concludes our presentation. Heather, back to you.
You're still muted, Heather. Sorry.
Sorry about that.
It's all right. Whenever you're ready.
Thank you very much, John, Steve. You've certainly given us a really great understanding of the costs and benefits that are associated with various options with regard to power augmentation in gas turbines, and in particularly it really quite clearly demonstrated why dry air injection really can offer some great benefits in this particular application. Now I'd like to sort of switch over to, I've got some great questions that I'd like to share with you. I'm going to start by start again, Heather. I'll kick off by directing my first question at Steve. Obviously, a lot of the presentation has been focused on the dry air injection system or technology being applied to existing gas turbines. Is it also possible to have it installed in new gas turbines?
Oh, absolutely. The technical principle is the same whether it's existing or new. On the new gas turbines, it will reduce the overall cost on a dollar per kilowatt basis of the new installation, because obviously at the cost point we're at versus the cost point of a full new power station, you are lowering the dollar cost per kilowatt and trying to make the output of that gas turbine plant constant across all ambient temperatures.
Thank you very much, Steve. And John, I was quite interested. Oh, is everyone hearing?
Yeah, I heard that's weird. Let's go back to thank you very much.
Okay. Thank you, Steve, for that. And John, were you quite surprised by the sort of fairly conclusive finding of the analysis that really the dry air injection really offered the operator their best ROI.
Actually, I sort of was. I was not too aware of the product prior to me doing this study, so it was very interesting to do this independently with GT Pro and see the results. So I was surprised, but pleasantly surprised, because the product does offer a tremendous ancillary benefits that are very important in the overall power market, such as being able to respond quickly and being able to provide full power output, basically at hot weather conditions, which is where power plants are rated, and they want to see that that rating and be able to prove it during performance testings.
Oh, Heather, you're muted. Sorry.
I thought I unmuted myself. Beg your pardon. And John, I think you said in your presentation that actually in the application that we were looking at, that there was an opportunity of actually increasing the power augmentation further. Are you able to kind of give us any figures in relation to that, or maybe that's something that Steve would like to respond to?
Yeah, the older gas turbines, which were at the Bali site, were designed with a lot more margin because of the uncertainties of without computers. They were probably designed, with the slide rule back then. So there's a lot of margins for safety and margins for airflow, and that margin could easily be tested. I'll say pushed once you put in the first few turbophase modules and see how much air the machine could actually absorb. And I don't know, Steve, you may have some additional numbers that you can get, maybe over 5 to 8% additional airflow on these very older units.
We have the data I showed for the 6B site outside of Chicago is with one turbophase module on a GE6B, that's approximately just shy of 5% air on an ISO day. The two modules, therefore, is just shy of 10%. We absolutely injected almost 10% air into a 6B, and doing so, we checked margins on compressor surge, on generator limitations, on shaft torque limits. All those things get taken into account before we do any activity like that, and as we showed, it's absolutely plausible and possible, and can be done, and with significant margins. As John rightly mentioned, the older machines have more margin built into compressor surge, but even the newer machines can take more than 5%.
Excellent. That's really great to both of you. And Steve, I mean, it certainly seems the whole turbophase system, it's based on this principle of simplicity is always best. Can you sort of give me an idea with regard to its installed base at the moment, and kind of where you've got some of your systems up and running commercially?
Sure, and I would love to tell you there's hundreds and hundreds of these installed, but it's a new product. As I mentioned, we're the first commercial dry air injection system. So the first product went commercial in the summer of 2014. So we're only 1 year removed from the first system being commercial. So we have installs in the Middle East, obviously in the hot temperature climates associated there in the summer times, as well as here in the US, and so far on the GE frames, ranging from 6B up to 7FA. As we continue to move forward with the Siemens frames and Saldo and Alstom frames and Mitsubishi frames, that opens up more of the market to us. But mainly it's a new product, so it's not as globally installed as we would like to see it, but we're working hard to change that.
That was very honest of you, Steve. That's great. I was interested to hear you mention that you have some systems installed in the Middle East, because I did sort of wonder if, obviously in Asia, there's a very high humidity, so sort of ambient temperatures there, whereas in the Middle East the temperature is much a drier atmosphere. And I just wondered if that had any impact on how the system performs.
No, it really doesn't. As we went through, we tried to be ambient independent. So whether the way our system's designed is we produce a certain amount of airflow, and that airflow is constant at all temperatures. And we do that by using a turbocharged reciprocating engine and a compressor system that has IGBs that we can change the amount of airflow into the machine. So we're modulating our system to have a constant airflow output. So whether it's 100, and sorry I speak in Fahrenheit is how I think, but if it's 120 F or 40 Celsius outside, it doesn't matter whether it's on the hot end, humid, dry, or if it's sitting at ISO conditions or colder on a humid day. Or our units in Chicago ran in a snowstorm in this past winter. So the humidity and temperatures and elevations even don't matter, because the gas turbine, our recip engine is with the turbochargers and our IGBs maintain a constant airflow.
Great. Obviously in John's presentation it was quite clear on a capital cost basis that dry air injection is very competitive. Is sort of PowerPhase's approach to kind of sell the systems, or are they also looking at maybe more sort of leasing options as well?
Well, that's a good question. We do both. I mean, every site has its own economic challenges, and so if capital is a problem for a customer, then we do have leasing arrangements set up. We have a leasing company set up to be able to do that, or we can sell the product. And then same thing with scope. If a customer chooses to want to use a local EPC company to install it, or would prefer to use us as a turnkey installer, we can do both as well. So we try to maintain a low cost point of entry, but if that capital is too much, then the leasing is definitely an option.
Great. And John, if I can bring you back into the conversation, obviously you've had many years of experience in the sort of asset optimization. Would you say that you're sort of seeing now a shift towards so the operators and the owners really looking to augment their existing gas turbine assets, maybe than necessarily building new plants? And if that's the case, I mean, what do you see are the major drivers behind that shift?
Well, we've seen definitely a lot of infrastructure reinforcements going on. The new introduction of microgrids for small, independent, and more decentralized usage of power generation. So, but from an owner's perspective, the power plant owners are looking to create more value for their existing assets, and this is an ideal way. Many times they'll add different hardware or systems to their existing assets to try to improve the return on investment. Some of that could be adding a black start diesel, but the PowerPhase unit certainly provides installation capability that can be done while the power plant is running. So it fits in very well with power augmentation throughout the globe, really, to try to improve existing bottom lines.
Thank you very much, John. Gentlemen, we'll obviously cut this out, but is there any other sort of questions that you would like to see us cover as part of this section? I'd sort of gone through most of the ones I had, and then obviously some had already been answered in your presentations.
The only thing I don't think I got to cover was lead time. So I'd like to, how long, a lot of the gas turbine internal parts may be, years or 18 months, 12 months to 18 months, and we're 6 months from order to commercial operation.
Okay, we can do that one. No problem at all. John, is there anything from your side?
Not at this time.
Oh, okay. Okay. I am unmuted. And Steve, I'd be interested to know what sort of lead times we're talking about in relation to having your own.
I'm going to have you do it again. I had a little drop out there when you first started the question. I was going to re-ask it. Sorry, I just didn't want to get you too far into it. All right.
No, that's fine. So I'm good to go?
Yeah, it looks good.
And Steve, I was interested to find out a bit more with regard to lead times. For example, if I wanted to order a turbo phase system, how long would it take?
Because we're using off-the-shelf components that are not designed specifically for us, that allows us to fall into a manufacturing cycle that's very quick. So we're a 6 month from order placement to installed commercial turnover to the customer. And so that includes all installation, commissioning, and testing, and turning over to the customer. So 6 months total time period.
That's very impressive. Thank you very much. Well, gentlemen, can I just say I've thoroughly enjoyed our discussion today. I think the presentations that have been given have been highly informative, and I'm sure our audience has very much enjoyed finding out about the analysis, and obviously, Steve, about your company's really quite interesting and innovative technology. Thank you very much.
Thank you, Heather.
Thank you, Heather.
I'm going to have you guys say thank you guys again. Thank you, Heather, again. Sorry, John, you go first.
Thank you, Heather.
One more time.
Thank you, Heather.
Good. All right. Steve?
Thank you, Heather. Thank you, John.
One more time, Steve.
Thank you, Heather. Thank you, John.
I know it's okay. Good job.
Thank you, Steve.
Good night, John boy. Good night.
Yeah.
Good job, guys. So now the process will be I'll start cutting these together. I will try to follow the slides just by what you were saying. And if I get something out of order or the timing isn't right, just let me know and I can make that an easy fix. And then I'll send the video to you, Heather, and you can forward it on, or I can send it to everybody and you guys can.
Yeah, I would say, Charles, you've got everyone's email address, so yeah, send the link over, and then we can all sort of have a look at it, and then obviously I suspect there'll be some changes that we'll just need to do. Hopefully it'll just be tweaks to make sure.
Charles, this is John. There's I noticed a few typos in my slide. Okay. So you want me to resend the slide show first before you look at it?
That'd be great. That'd be great.
Just you don't have to worry about typos then.
Yeah, I found a couple of mine, so I just done it while we were talking here too. So
that's perfect. Just send that to me, and I'll just delete the old one. And then so we talked a little bit about you guys being really small in the corner when the presentation's on. So when it's not on and you're just kind of having a little bit of banter, just conversation, you'll be full screen back and forth. Just FYI. And then I'll put an intro on it. Then John, you wanted to change the title of this, whatever we want to call it.
No, we're keeping the title.
Oh, we are keeping it. Okay.
Yeah.
So whatever we're going to call it, just I'll put that in the intro. I'll make like a little build and some music, and make it easy.
Guys, am I good?
John and I put together a slide yesterday that had both of our logos and names and phone numbers, emails on it. If we can get that somewhere in the end of it or something, or contact information, that'd be great.
Sure thing. No problem at all.
Yeah, and will there be possibility of actually, I know it's not your job, Charles, and it's not Nick's either, but on the page that people are viewing the so we'll have the video player there. Is it possible to kind of just get some extra text there saying if people have any other questions, please contact?
Yeah, I wouldn't.
As well.
Why we couldn't do that at all? I mean, I don't. I'll ask Alex. Whoever designs the actual page layout for the email blast.
Yeah, that may be Lane as well. So I guess that's just one question. John, Steve, are you happy to have your email addresses there, or do you want it to go to sort of generic email address?
I'm good with my phone number and email.
That's fine then.
Yeah, that's fine. I have no problem with it.
Great.
All right, and then Nick, if you could just send me the YouTube link, and I'll download it and get it going from there.
Sure, of course, yeah. I'll do that now.
Thanks for all the help, Nick. I appreciate it.
Yeah, of course.
Absolutely, Nick. Thank you.
Am I good to stop recording? Is there anything we need to do over again or anything like that?
I think that's it. Yeah, we can stop.
Okay.
And guys, thanks for all the cooperation and all the help. If you have any questions or, like I said, if something's not right, don't hesitate to email me. So we'll get it going.
Hey, Charles, I fumbled a little bit there. I guess when I repeated things, you just